Hello and welcome to lecture 8A, which is a extension of lecture 7 and 8. We have covered number of wear mechanisms, and this topic of the lecture 8A is the role of fatigue and fracture mechanics in wear debris formation. So, these mechanisms which we are studying of fatigue and fracture, in my view, they lead to form wear debris. It's a bit different, that is why I felt that maybe we should have a complete lecture for this purpose. Now, when I think about the fatigue, what comes in our mind? Something like a reversible loading, something like a reversible stress, and that is why it has been shown over here that in this case what we are showing stresses, and then here we are showing the reversible also. Is something like there is a maximum, then minimum, then maximum, then minimum, and then the stress magnitude varies between the delta sigma. We have maximum value of the stress, we have minimum value of the stress. Now, this minimum value can be 0 also, I can say sigma minimum can be 0, or sigma minimum can be negative of maximum also. So, there is like a tensile and compressive stress, it is possible, but it comes in a natural way when we think about the fatigue. Again, then we have 4 known theories to explain the fatigue process. SN diagram or SN criteria is well known. Sometime we, instead of going for the stress and number of cycle, we think about a strain life cycle, strain and number of cycles. And what we, as we have already entitled, obviously the given entitle the fracture. So, that is a fracture mechanics point, that fatigue causes some sort of brittleness in a material, and that brittleness initiates or maybe say propagates a crack. So, we should think from a fracture mechanics point of view. And last one in this case is a probabilistic approach. What is the meaning of probabilistic approach? There will be a number of problems in a material, now maybe whatever the design way we are doing, there will be some sort of loading related probabilistic approach. So, inherently in a probabilistic approach, what we assume, everything is a dynamic, everything is a reversible kind of thing, there is a load and unload continuously happening. So, that is what we understand from a probabilistic approach. We consider this as a completely statistical approach. Another title indicates that in my view, I assume that this mechanism really can explain wear much better manner. Fatigue and fracture, these two mechanisms will be able to explain the wear phenomena in much better manner. Reason being that these two phenomena are really trying to separate wear debris from the main surface, from a parent surface. So, that is why these two mechanisms play important role in my thinking. Now, another point comes when I talk about the fatigue is something like, is a surface fatigue or is a subsurface fatigue. In my earlier lecture, I mentioned that maybe 70 to 80% times the fatigue starts from a surface because of some sort of discontinuity. However, there is a possibility of the subsurface cracks or subsurface fatigue also. We will explain to some extent in this lecture also on this. Another one that I mentioned that many times fatigue causes the brittle fracture. It's even the ductile material, because of the repetitive cycles, the material behavior changes, brittleness increases, and that it causes the fracture. So, we will deliberate to some extent on that also. In some time, instead of the stress or the load, we say that it is a sliding. Quite possible under the sliding some sort of a contact happens, and because of contact the load happens, and we can represent the fatigue phenomena in terms of reciprocal sliding, or we say even the unidirectional sliding. I will just take the example of my hands. You say I have 2 hands now, and I start sliding one hand on other hand. What will happen? I will have some sort of asperity in one of my left hand and asperities on the right hand also. So, contact will happen only during the asperities, and the one asperities loads other asperities or maybe say the material, and when it passes there will be unloading of that. That means, during the sliding, loading and unloading will happen also. that can be related to sliding, and if we know exactly the magnitude of the load or maybe the load magnitude, then we can think about the load related thing. Otherwise, we can express in terms of the sliding, in terms of the relative motion. Now, as I mentioned, the fracture mechanics is related to crack initiation and propagation. Question comes, what is a crack initiation? We have deliberated this in one of our earlier lecture, but in my view, crack is always there in a material. It can be a kind of the boundaries, we say that different kind of crystallization, or maybe the polycrystallization, or maybe the when we are trying to alloy the materials and we do different materials, then cracks will be there, inherently cracks will be there. Only question comes, what is the size of a crack? Is it a nanometer, is it a micrometer, and then do we have a sufficient energy, do we have sufficient load, sufficient velocity, which is getting imparted, the energy is getting imparted to the crack, and the crack will propagate or will initiate increase in a size. So, this is what we are thinking. If I try to express in another term, what we say, the fatigue occurs in practically all mechanical units leading to the localized progressive degradation. Here I am again emphasizing there is a localized, reason being asperities whatever we are thinking is these are localized one, where aspirity to asperitic contact happens, that is a localized contact. So, we are thinking in this course only that localized progressive degradation that eventually leads to the mechanical unit breakdown. There will be as I mentioned there will be inherent cracks in practically all the mechanical system, and fracture mechanics approach considers how cracks will be propagated. So, that is why it is important, that is why we are connecting fatigue and fracture as one of the part of the lecture in this case. And then another point then we can detail maybe when we think about the failure analysis, the lecture on the failure analysis, we can think about how it will impact the fatigue life or maybe the life of the component or life of the system. Now, science of the mechanisms of the wear debris creation may be understood. In my view, we can think about the wear debris creation in terms of the crack initiation leading to the surface and getting separated from a surface. So, in my thinking, the fracture itself is related to the wear debris. We do not want a complete failure and then say it is a fracture, but if the wear debris is getting separated from a surface, in my view that itself is a fracture. Now, if the theory can be really used to explain the wear debris generation, that will be very good. That is why we are trying to explain from that point of view. Reason being, we need to focus, if the theory is clear, then we need to focus that how do we prevent wear debris generation, how do we minimize, how do we go for the ultra mild wear domain. So, the life of the component is improved, or how do we minimize the surface degradation. These things are important. Now, when we talk about the fracture mechanics, in my view there are many factors, but two very important factors are something like a stress intensity factor. What is a stress intensity? Can we really minimize the stresses? Like surface roughness itself creates a stress intensity, or maybe the concentration of stress at the few location. So, that is why in our earlier lecture we say that please keep smooth surface, minimize the asperities, minimize the surface roughness. And of course, when we design a surface, so when we think about the coating and surface design, we will be again deliberating on this topic. Another one, the important aspect is the crack growth rates. So, if the loading in a manner is something where the crack is already aligned, naturally it will grow much faster pace. So, can we really design a surface where the crack growth can be checked? That is, these are the two important aspects from fracture mechanics point of view. I mentioned something about a probabilistic approach. We say the probabilistic approach assesses the component or the structure dependability and safety against a fatigue failure. So, we are completely coming with the probabilistic approach. We feel that we do not have all the information. So, we should go have the probabilistic approach. Now, what we consider here, we say that the statistical fluctuation in material property will be there. That is why we say there is a lower limit of the material strength and upper limit of the material strength, and then we come up with a mean value and some sort of deviation. That is what we present in the material properties. That will always be important. Similarly, there will be loading condition, a statistical distribution of loading condition. There will be max value, there will be minimum value, and there will be some sort of a variation, mean value and plus minus some variation. distribution. So, that is why these all are the fatigue related. Now, even coming to the surface profile, again we have realized that surface will not be extremely smooth, again there will be some sort of a statistical distribution. In fact, the friction which happens between the two surfaces, that itself is a statistical, where which happens between the two surfaces, that is also statistical, and that is why many times we say that we need to repeat and repeat number of experiment, maybe say at least 3-4 experiments to come up with the right results, because these are the statistical properties, and we should come up with mean value and some sort of standard deviation. These are the influencing parameters. For that purpose we need to study. Now, we have covered already this topic. I am just trying to repeat, so that now we can connect what we are proposing in this course. We have already covered the fatigue and we have also covered the fracture, but two independent way. What was covered in the fatigue? We say there is some sort of the two surfaces will be coming in a contact. So, if I say this is surface 1, this is surface 2. Now, they are coming in a contact and relieving. So, maybe this can be this ball can be a simple asperity, it can be a really solid mass, or maybe it can be other shape also instead of the spherical shape. So, when it comes in a contact and then relieves back up, what will happen? The component is getting compressed and then getting relieved. That means, whatever the residual stress again will be relieved, and then there is a possibility of a crack initiation or the expansion. So, another thing which I mentioned here that these are the if you see the small cracks are available in this case. So, these are inherent in material, all the materials will have this kind of maybe say nano level cracks, and then when the loading and unloading is sufficient to increase the size of crack, that is what the increased size of the crack has been shown over here. And finally, merging of the 3-4 cracks also, maybe the 2 cracks get merged and become a big crack, and when this bigger crack also leads to the surface, then it will come out with the wear debris. So, this is the WB, that WB is a wear debris coming in this case, or we say the wear debris will come out from this. This has been already explained to you in earlier lecture. We say step leading to generation of wear debris. We say normal load is applied, which will induce high stress when contact point comes, and then because of the high stress there will be plastic deformation. Again, this is another important aspect. Many times we design a component, assume that only there will be elastic deformation, but that is not correct. Initially, at least there will be some plastic deformation, because asperities will come in a contact and stress level will be more than the elastic limit. There will be plastic deformation, and then that is why we say there will be plastic deformation. Now, question comes whether plastic deformation will be there always. Quite possible the surface will change its configuration or deformation in a manner, work hardening will happen. Quite possible initial high stresses, and maybe after a few cycles it becomes under lesser than elastic limit also. Those things are also possible, like initially very high asperities or high surface softness, after sliding for some time the asperities will be reduced, or maybe say the height will be reduced. Then again the stress distribution will be far better, maximum stress will come down, then we can say that it is possible initially the plastic deformation, then after some time it gets converted to elastic deformation, that is also possible. However, if there is a plastic deformation continues, it does not come back to the elastic deformation, then running in period will be 0, and then we will be getting the some sort of continuous deformation, and that will also create some sort of a subsurface crack. Maybe if there is some sort of the initial very nanometer level some sort of discontinuity, that will increase in a size, and we can say that it will be a crack nucleation, or maybe it will be sufficient to start expanding, and that is why we say that it is a early growth of the grain size as a crack formation. So, that already there is a discontinuity, maybe the grains are there, but because the loading, or maybe because of the plastic deformation is there, and that is increasing the chances of crack growth, or maybe it is really giving some sort of an initiation for the crack formation. Once the crack has started, after that we cannot avoid it. We say the expansion of crack will happen due to the reversal of the stresses, or maybe sliding, or maybe the loading in a manner. So, that is possible, and finally the wear particle will come out, and this diagram also was shown to you. We found we say that there is some sort of sliding in this direction, and maybe I can assume there is some sort of spherical ball on the surface, and then there is some sort of initial cracks in a surface. So, there is a normal load on the surface and as well as a sliding. So, what will happen because of the compressive stress and because of the tangential direction load, there will be shear stress, and we know very well if the coefficient of friction is negligible, then the maximum shear stress will be subsurface below the surface. However, if the coefficient of friction increases and there is a more and more resistance in a sliding direction, then what will happen, that the maximum value of the shear stress will be on the reaching to the surface. When it happens, quite possible the wear will the wear debris particle will come out, and that has been shown here. The fatigue wear or the pitting on the gear teeth was demonstrated. So, there is a one pit here, there is a number of small pits on this side. So, this is a possible in this case. Now, coming to the fracture, we again the similar kind of thing. There is a first we required some sort of nucleation. Now, nucleation can start from a stress concentration, some sort of discontinuity where the stresses will be high. Wherever there is a discontinuity, we know that stress concentration will be there, and that can lead the initiation of the crack. Once the crack is initiated, then propagation will happen because of the loading situation, and finally it will lead to the failure. But we are not considering the failure of the system completely. In this course, we are assuming only the failure of the wear particle which is coming out of the from surface. So, we are not going to think complete failure of the system is basically a separation of a particle, separation of wear particle from a surface, and that is what we say it is connected with the fatigue and fracture. So, fatigue and fracture are causing some sort of a wear debris generation, that is what our thinking. Now, this is the same thing will happen. We have studied some sort of fracture, the cleavage we have shown in earlier one. There is a micro void fracture also, that is the dimples were shown in earlier slide also. Even the intragranular we say the IG crack fracture also been shown that there are the cracks which we are able to see when the granular grains are separated, and then the crack expands across the grains. So, that is what we call as a intragranular crack formation. Now, we also study something like a radiation and heat. What we studied in that, there is a possibility that localized heating occurs. When there is a localized heating, localized plastic deformation may happen. There is a possibility of some sort of atoms will be escaped from the surface, and because of the escaping of the atoms from a surface, we study that there will be possibilities of cavities, there is a possibility of cracking, and there is a possibility of the swelling of the surface itself. All this is are going to give us kind of initiation of the crack, or maybe the increasing the chance of the initiation of the crack. Of course, there is a possibility of the melting because of the excess heat. When there is a excess heat, naturally again when the solidification happens, there will be irregularities, and that will also give us some sort of chances to form the crack, and that is really harmful as such. So, we should avoid exposure to the radiation or the heat, and maybe we should have a control. This diagram also was shown here, something we say the micro fatigue crack formation due to radiation occurs. You can see here that the thin lines, and then with the more exposure, significant damage, you are able to see the deep lines also. So, this is a kind of a cracks have propagated to the surface is causing the failure, and in my view all are the leading to the are related to the fatigue and the fracture. Now, it can be low cycle, it can be a high cycle fatigue. Everywhere that there is some change in maybe load, or maybe the maybe the material property or crystallization, or maybe say the every crystal whenever we are trying to connect, maybe use improve the properties of the material, we try to ally the material, and that also gives us some sort of crack formation. So, what is the overall aim of this course is to understand, we say that how to find onset of the fatigue fracture from atomic level discontinuity, because atomic level we know that discontinuities will be there, to the irreversible fatigue. Once initially like elastic limit, we say that it is a reversible load unload, it will remain in reversible condition. But once a crack has initiated and started propagating, then it will turn out to be irreversible state of fatigue, and that we need to really keep check on that. However, there is a lot of knowledge gap whatever is we think about the theories, everything theory has some sort of a shortcoming, and then we do not have a complete knowledge. So, we take theory and experiment, we combine, we say that exclusively theory will not be able to give all the results, exclusively experiment will not be able to give all the results. So, we need to combine these two to come up with the right results. That is why we say the knowledge gap to precisely quantify impact of the microstructure on fatigue fracture formation is not available. So, complete theories are not available, may be available for the few components or maybe few subsystems, but it must have been done after doing extensive experiments on that, maybe validation. So, that is why we require experimentation or experimental studies along with the theory, along with the understanding. And when we think from atomic to the molecular structure level, we know the scale difference is a huge. Sometimes we talk about a nanometer level, and when the component is like level or meter level, naturally 10⁻⁹ difference. So, how do I make a theory with the atomic level which is valid for the macro level or maybe the level. So, we need to think about a combination of the different theories connect and then maybe do experiments in between to validate and connect this. So, that can be done only when we want one or two systems to be perfect, but cannot be generalized. That is some sort of a shortcoming, but still we require a knowledge to come up with that. And some more details have been given in this reference, which we picked up the material from this reference. So, you can go through this reference also. Now, coming to the what we say, there is a huge difference on a scale level. That is why we say the scale length scales are huge. Like when you think about atomic level, we are talking something like a 10⁻⁻10 meter level, that means 0.1 nanometer side. Then there will be a location, maybe when a grain size and all, there will be dislocations also, and then the dislocation we are treating something like a 10⁻⁸ meter level, and then there will be some sort of pattern also, and that has been shown the pattern of the dislocation, that is on the level of 10⁻⁷. When we think about the polycrystallization, it again can be homogeneous. It has been shown in this case a homogeneous kind of thing. It can be heterogeneous also. That is the order of 10⁻⁵ meters. And then finally, when we talk about our solid material, is something like a 10⁻³ is a 1 level, where we can really see the plastic deformation. So, plastic deformation at the lower level will not be able to see. And when we do simulation, even do a molecular dynamic simulation, we need to start from this 10⁻⁻10 level and then reach to this level. Naturally, it cannot be done exclusively on a theory basis. So, what we really require some sort of a model as well as a experimental work. In this case, what we are saying that this microstructure sensitive computational modeling, it has been taken from a reference, it has been shown here. This is, you can see, microstructure sensitive computational modeling of fatigue crack formation, which we have picked up from literature. And then this model considers the impact of material microstructure on initiation and propagation of the crack. Again, it gives us some information, it does not give complete information. The reason being the fatigue fracture formation is impacted by distribution of inclusions. If you do not include inclusions, you do not consider probability of inclusion, it may not, model will be valid only for 1 or 2 kind of material or 1 or 2 case studies, but it cannot be generalized. Then it has some sort of dislocation, every material under different load condition may be forming this dislocation. If you do not have a knowledge about the dislocation, then there will be problem. Even the pattern of the dislocation that has been shown here, the pattern of dislocation can be changed, maybe will be different. Another thing, what is the size of the grain? It can be a smaller size, coarse size or fine size, depends on the heat treatment, depends on how we are manufacturing or processing it, depends on that. So, that is also will be the affecting it. Even the heterogeneity among the grains, some grains are smaller size, some grains are bigger size, or maybe different material, it impact, and modeling this is not possible easy to do it. However, if we have some sort of microstructure data, like some sort of a grain boundaries, a grain orientation, which we can really take from XRD or the microscopic material, microscopic technique, which we will be studying later, and then you give a data to the model. So, model has to assume some sort of pattern. We need to perform experiments on that, get those results from experiment, again embed back to the model. So, models cannot be generalized one, it has to be working in tandem with a experimental setup. That has been shown in this slide, and it is important for us to really think from that point of view when we want to avoid corrosion and we want to avoid some sort of surface degradation because of whatever reason. So, but we need to really keep these things in mind. Now, how do we do that is important. As I say, detailed modeling is difficult for us. So, for simplest one, what we do, we say that to understand the behavior of material under fatigue loading, we can divide in 3 categories, and that is the easier one. We say what is the first category, plastic strain accumulation will occur, and then we can say that this is a continuous plastic ratcheting. That means a number of cycles have been developed, and then we know that the last time we have seen the pattern of the fractures, we find number of patterns on the surface and the cleavages on the surface, even the beach marks on the surface, and that happens because of the plastic ratcheting. That means stress level is very high beyond elastoplastic limit, and then that is continuously happening, and there is some sort of plastic strain which is getting built up on the surface, and finally that whatever the ductile fracture will get converted to the brittle fracture, and that will give a failure of that. So, another one is reversible cyclic plasticity. Now, you can see here the load is decreasing, then we can go with this kind of pattern. It will give a longer life, maybe say more number of cycles compared to the plastic ratcheting. Well, if we further reduce the loads, then we are getting elastic shakedown. Now, elastic shakedown does not mean the stress level does not come to the plastic limit at all. It comes, but what will happen in this situation? Initially, asperities are in a contact, plastic deformation will occur, asperities will change their shape and then increase the area of contact. When the area of contact is increasing, naturally the maximum stress will come down. Quite possible maximum stress comes slightly lesser than the yield limit. If that happens, then we say the material is mature enough to sustain the load, and it can really come up with an endurance limit. That is what we in the fatigue limit we use the word endurance limit. That happens exactly in this phase when the elastic shutdown happens and the stage has been crossed. That is where, however, the load is in this case we can say the minimum compared to the reverse cyclic plasticity or plastic ratcheting. Plastic ratcheting is a maximum, that the failure will occur, and quite possible it will change from ductile failure to the brittle fracture in this case. So, instead of going to the so much detailing, we can divide in 3 categories. We say elastic limit, and then reverse cyclic plasticity and plastic ratcheting. However, I just want to connect this with our mechanism which we have studied, something like a bathtub curve. You know that this is a complete the bathtub curve. We know that A to B, where will be maximum, or the B to A is where is maximum. Now, why it is happening here? At the A level, the many asperities, maybe the few asperities come in a contact, and the stress level is very high. Now, with the sliding, what happens that asperities will change the shape. It can be like initially very sharp peaks, it will be slightly plastic, under plastic deformation they are getting some sort of contour at the bottom. Because of the contour, what will happen, angle the projection angle or cone angle will increase in a size. That is why the where it is coming down. After that, it is coming something like elastic shakedown kind of thing. That is what I am trying to say. The BSC can be kind of elastic shakedown, it can really sustain the endurance limit, it can really save the number of cycles in this. And finally, it can come something like in the plastic ratcheting, or the area of contact is much lesser, the stress has gone again very high, and then the failure occurs. So, that is why I am trying to connect the fatigue and fracture with the wear phenomena. Sometimes people say these are unconnected. That is why I say there may be a connection between the elastic shakedown and running in wear behavior, and that is what I am able to understand from here. We say elastic shakedown leaves a residual stress on the material surface, which improves its running in the wear through micro hardening. So, sometimes people use the word micro hardening, or sometimes we will use a word at the bottom instead of the sharp peaks, and we are getting the rounded edge, and because of the rounded edge the wear will come down, or we are telling that this is micro hardening. Heat treatment has happening at the local level, and it is increasing the hardness. That is why the wear is coming down. Whichever manner the wear comes down from that point of view. Now, because of the rounding of the asperities, what we understand, there will be a sort of the load redistribution. Now, because of the load redistribution, what will happen? Maximum contact pressure will come down. So, that is why the contact pressure distribution happens in better manner, more number of asperities come into contact, and then they have a round shape at the bottom, and then they are able to distribute load in better manner. Maybe we say instead of single asperity, there are many asperities, and then coming into contact, and they are rounded. So, they are not really giving a lot of friction force, and then the wear is significantly reduced, and chances of elastic shutdown increases, and that is why we say that the material will go through the fatigue fracture, not the immediate failures or immediate the fracture. So, this is why the fatigue is important. Most of the time when we think about a wear coefficient, we say wear coefficient should be, acceptable wear coefficient should be lesser than 10⁻⁷. That means the number of cycles should be those many. So, the material really pass through each other. That is what the wear coefficient, and we try to relate earlier probabilistic the probability of the failure or probability of the wear debris generation. That is the way we are connecting. If we think from this side, we are able to connect fatigue, we are able to connect wear, and if we have understanding of these two phenomena, fracture can be controlled well as per the way we want. So, this is what we say, it is what we can control the wear behavior, and we can minimize the stress concentration on that. Just to elaborate whatever I mentioned, I am again picking up the slides from a previous lecture. The lecture 4A slide 3 was we try to show that this cone angle, and if the cone angle is increasing in a size, the cone angle is increasing in a size, or we say asperity angle is increasing in a size, then the wear rate is continuously decreasing, and that was initial what we say that curve of running in behavior, to demonstrate the running in behavior. To elaborate this in more way, we say that when asperity angle is a 60 degree, you can see the rounding edge is not that much, area of contact will be lesser, while when the angle has increased to 100 degree, there is a possibility when it goes tip, because in this case naturally some sort of penetration of the asperities will happen. When the penetration happens, the area of contact will increase in this case, particularly because of, and moreover it will be smooth transition, it will not be like a peaks are going inside, it is the rounded edges are going in this case. And then if further increase, what will happen, stress level will come down, this 2A level increases, maximum stresses are coming down. Now, maximum normal stress comes down is a one thing, but in addition the shear stress also will come down in the magnitude. So, these are the favorable situation for us. And we say that in this situation what will happen, the cracks can be controlled, whatever the initiation of cracks may not be able, what we say completely controllable, but propagation can be controlled because the stresses are coming down. So, this is a very important to understand what is the connection between fatigue fracture and wear. In my view, they are interrelated, and fracture we need to think from separation of the debris particle from a surface. We do not have to think from the complete fracture or complete separation of the material through and through thickness, it is not. We need to think from the debris which are getting separated, and what will be the, from where the debris will be getting separated. This again I am taking the slide, the figure from my earlier slide. This figure was shown, you say whenever there is a loading and unloading and tangential load, what will happen, this top layer will be highly deformed, and then strains is so high that this can really create initiate some sort of a separation. So, there is a possibility of the dislocation, or maybe say separation or delamination of this layer, that can be explained using the fatigue phenomena also. So, if there is some sort of subsurface crack in this, there is a possibility this sublayer, this thickness can be removed, can be delaminated from a surface, and then that is what we need to really think about, how to really minimize this surface deformation to that extent which leads to the separation from a surface or getting delaminated from a surface, or because we have said already in this case cells are in a vertical direction. Here there is some sort of orientation, while top layers are completely directed towards a sliding direction. So, this direction goes perpendicularly. Naturally, there will be more and more dislocations. When there are more and more dislocation, there will be chances of the crack initiation and crack propagation. So, finally, we need to think about this top layer, how to minimize this top layer, and then keep a minimum stresses, and then how to avoid a separation of this layer from a surface in terms of the wear debris. That is what will be continued in our next lecture. Thank you.